Assalamu alaikum, dear students. In the last lesson, we were talking about amplitude, period, and frequency. We said amplitude, it is the maximum displacement from the rest position. And then after that, we talked about period. We said it is the time, we can say the time for one complete oscillation. You could call it oscillation, vibration, or wave, doesn't matter. And then after that, we were talking about frequency. We said frequency, it is the number of vibrations or oscillations per unit the time. And we also studied the relation between frequency and period as well. And then we ended up right at this question here. So now this question here, the first question in the section review says what? The reading on a metronome indicates the number of oscillations per minute. Don't forget this per minute thing. All right, so the question is, what are the frequency and period of the metronome's vibration when the metronome is set at 180 oscillations per minute? I need you to focus on this thing right here. It says 180 oscillations per minute. Isn't that the number of oscillations? Yeah, so when it comes to frequency, we said we have two equations to do that. We can either use frequency, it is equal to the number of oscillations or vibrations or waves, it doesn't matter. Oscillations, all right, per unit time, or we can say frequency, it is equal to 1 over period. Since we don't have the period given here, so this is, or the number of oscillations given, so this is the equation that you're supposed to use. So we can say frequency now, it is equal to what? It is equal to the number of oscillations per unit time here. But don't forget, so how many oscillations do we have? It is 180 oscillations. You could be given vibrations or waves, doesn't matter. All right, and then it says per minute. What does per minute means? That means every minute. And you do know that every minute it is 60 seconds, right? So you can cancel out or simplify this. That is going to be what? Going to be 3 hertz now. All right, so now if you found the frequency, can you find the period? Yes, because we know that frequency, it is equal to 1 over the period. And if you want to find the period, just cross multiply or swap their places here. So period, dakata, frequency, sorry, period, it is equal to 1 over frequency, which is going to be 1 over 3, and that is about 0.33, and then of course it repeats, and that is going to be seconds since it is the period here. That is how easy you can solve questions. All right, now we have another question here. By the way, you can say number of waves or oscillations here instead of this one here. So just say number of oscillations there. It makes it easier to solve this one here. Now, the next question that we have says what? If you shook the end of a rope up and down 3 times every second. Now, let me tell you regarding this one here. So the question says, each second, what would be the period of the wave set up in the rope? And then after that, what would be the frequency? Now, let me give you an idea regarding this one here. Okay, so the question is asking what would be the period and frequency. So I need you focus, or first to focus on this one here. All right, let's zoom in a little bit. Okay, so what is the question saying here? It says if you shake, see, we have a rope, all right? So here's a rope. You're going to shake it up and down here, right? We know that if you shake it up and down, every time you do that, there is going to be a wave moving or generating in a wave. But how many times are you going to do that? You're going to do that 3 times. So 3 times up and down in 1 second. So the first thing the question says, what is the period? We know that it is easier to find. Of course, you cannot find the period unless you find the frequency first. So we'll say frequency, it is equal to what? It is equal to number of, by the way, you can say oscillations, vibrations, waves, shakes, doesn't matter. So number of, we can say again, oscillations, all right? Oscillations, all right, divided by the time here. Okay, so once again, frequency, how many times? It says if you shook the end of a rope, how many times? 3 times each second, 3 times per second. We can just write 3 waves here every second. So now the frequency, it is equal to what? It is equal to 3 hertz. If the frequency is 3 hertz, what is the period? 1 over frequency again, 1 over, we can say 1 over what? 1 over 3, that is going to be 0.33, and then of course, you could continue, and then this is going to be second. So this is how you can do that. So the keyword here says you shake the rope up and down 3 times. So this is 1, this is 2, and this is 3, that is in 1 second. So this is, of course, the key to find the frequency there. Okay, the next thing that we have, what is the next thing? Let's solve these questions together. The first question that we have says what? Says, what is the frequency of a pendulum if it makes what? If it makes 36 cycles. How many cycles? 36 cycles. Let's zoom in this one. It says in 3 minutes. So how do you solve this question? These are the same method that we did previous times here. So frequency of a pendulum, frequency it is equal to what? Since you're given 36 cycles, it's the same as 36 waves or oscillations. So we'll say number of oscillations, or here we can just go ahead and write cycles if you want to. Cycles, right, per unit, the time here. So the frequency it is going to be, or the waves of the cycle is going to be 36, and then divide by 3 minutes. Don't forget, don't just divide by 3, because it has to be divided by the time has to be converted into seconds. So 3 minutes, every minute it is 60 seconds. So you do the math, of course, you'll get 0.2 hertz, and that is the frequency. What if they were asking for the period? Period would be 1 over the frequency. So that is going to be the answer for this one here. So you could just circle this one here. You could double check if you want to with a calculator. Let me double check that too, just in case, Yani. So 36 divided by, divided by what? Divided by 3 times 60. That is 180, right? The answer is going to be 0.2 hertz, and that is as easy as this. All right, what about the next question that we have? This is also interesting. The next one says, what is the period of a pendulum if it has a frequency of just 1 hertz? All right, so once again, we have the frequency, find the period. Period decata, 1 over frequency. So once again, period decata, what is the frequency? It is just 1 here. So 1 over 1, that is 1 second. That is the period of if for an object or whatever, if it has a frequency of 1 second. What did I just say? If it has a frequency of 1 hertz, all right? So the period it is going to be, or it is equal to 1 second here. Now we have this interesting question, which is very interesting, says what? If a pendulum is adjusted so that its frequency changes from 10 hertz to 20 hertz, all right? So its period will change from t second to what? If you remember, we said whenever it says a frequency or period change or one of them change and ask you to find the other one, the easiest method to do this is to write the equation of frequency and period this way. Do you remember we said it is best, for example, you could write this one. Let me just start from the beginning. Frequency it is equal to 1 over period. And if you cross multiply, then of course, frequency times the period it is equal to 1. Masha? So in this case, you can see that the frequency changes from 10 to 20, right? Can I say the frequency is doubled? You can see that 20 is twice as 10 here. So if the frequency is doubled, we always do this, right? So by whatever the factor is increase, we'll just make or change that into a fraction. So double that will be 2 over 1. Then the period is going to change by the same amount, but the reciprocal of this. So the period is going to become what? 1 over 2. In other words, if the frequency is doubled, then the period will change by 1 over 2. So that'll be the period here. That is 1. So which do we have this in the options? Let's take a look at the options. So it says t over 4 second, t over 2, 2 seconds, or 2 times the period, 4 times the period. We can see that the period decreases or becomes period over 2, and that, or B, it is going to be the correct answer here. Why is it not writing? There is something. Let's see. That is the answer here. All right, that is regarding the period and frequency. Okay. Now, what else do we have next? Okay, now the next thing, we have something very interesting, and that is the period. Let's just remove this one. The next concept that we're going to talk about is something very interesting, and that is the period of a simple pendulum, all right? And of course, it says the period of a simple pendulum depends on the length of a pendulum and the gravitational or free fall acceleration. So what exactly is this? Now, previously we were talking about period, right? We said period, it is it is the time that it takes for one complete oscillation, it is measured in second, right? We also learned that period and frequency are inversely proportional too. But if we have a pendulum, for example, so the first thing we're going to talk about the period of a pendulum here. So this is the equilibrium position. Let's say here's the mass of a pendulum. This mass that is going to oscillate. We said the time it takes, right, from the starting point, that would be point A, to go all the way to the other end. Let's call it point B here, and then back to point A. How long does it take? That is one period, or that would be the time for one oscillation. But how long does it take, or what would be the period here? Then, of course, we have an equation to find the period for a pendulum here. And the period for a pendulum, don't forget, we can say period for what? For a pendulum. All right, the period for pendulum, we know that period, it is represented by letter or capital T. It is equal to what? It is equal to 2 pi, the radical of L over gravitational acceleration. You can write it this way, or you could just erase this one and write G here. I prefer this one. The book uses I sub G. That doesn't matter. That as long as you know that this is gravitational acceleration. And don't forget, this period is measured in second. All right, so based or according to this equation, what does the period of a pendulum depends on? We can see that it depends on the length of the string. So here's the length, okay? And also it depends on what? Depends on gravitational acceleration, G, on that location here. So, but in a pendulum, you do know that we have angle theta. You can see we have the mass of a pendulum. Does these or are these going to affect the pendulum or the period of a pendulum? We're going to find out soon here. All right, so now this is the period of a pendulum, right? So we can see, or if I ask you, what does the period of a pendulum depends on? It depends on the length and gravitational acceleration. Well done, very good. So now, if I say, what are the things that can affect the period of a pendulum here? All right, so we'll say the period of a pendulum, it is directly proportional, not just the length here, so it is directly proportional to the square root of the length here. And of course, based on this, there is a question here. If we double the length of the pendulum, will the period be doubled? A lot of you might say, yes, if we double the length, the period will be doubled, but the answer is no, right? The period is going to increase by the square root of 2 here, because by whatever the factor, the L is changing, so you're just going to plug that into a square root. For example, if the length is doubled, so we'll just say 2 times, right? Or you can 2 times the length in here. So the period is now going to increase by the square root of 2, which is 1 point something, you can say. If the length is quadrupled, yani increased 4 times, all right? If it increased 4 times, then the period will be doubled in that case, which you already know that. So this is regarding the length, right? The relation between period and length, it is directly proportional to the square root of the length in here. What about the gravitational acceleration? You know that gravitational acceleration on Earth, or free fall acceleration on Earth, it is 9.81 meter per second squared in here, right? But what if we change the location, if we go from one place to another, whether if it is on Earth to, for example, a top of a mountain somewhere else where the gravitational acceleration change, right? Then that, of course, affect the period too. What if we go to the moon? Then, of course, that affect the period. So what is the relation between period and the gravitational acceleration? We can say that is inversely proportional to the gravitational acceleration. Don't forget this. Okay, so this is directly proportional to the square root of the length, and this is inversely proportional to the square root of the gravitational acceleration. But in pendulums, of course, we can have other factors too, right? So you can say this is one of them, this is the second one of them. And then what about the next thing that we have? We've learned that previously that frequency and period are inversely proportional, yes or no? So will the frequency affect the period? Yes, based on this equation, we've learned that. So we can say period, it is equal to what? 1 over the frequency, or vice versa in here. Okay, so this is the equation of a period in here. Okay, so by the way, what if I want to find the frequency there, right? So now you can see that these two affect one another, but don't forget. So now if I want to find the frequency, how can I find the frequency knowing the period? We know that frequency, it is equal to, by the way, at this point, if we can find the period, we can find the frequency. True? Yes, very good. All right, in the previous example, if you remember, we were finding the frequency by knowing how many waves are in a certain time. So we were finding the frequency, then after that we were finding the period. But now we can do the opposite. We can first find the period, then after that we can find the frequency. Basha. We know that frequency, it is equal to 1 over period 1, yeah? But what is the period equal to? Can I just replace this equation there? Yes, so that is going to be 2 pi multiplied or whatever in this case here. Now, this is the radical, which is going to be L over G, right? But of course, you don't have to write this one. You could just write it here, 1 over 2 pi times the square root of, if it is at the bottom of a fraction, if you're going to, for example, bring it up, of course, you'll have to take the reciprocal, which is going to be G over the length in there. But you really don't have to memorize this one here. So we could just say that you can easily find the period first, then you can find the frequency. If something affects the period, of course it can affect the frequency too. If it doesn't affect the period, it will not affect the frequency, and that's it. Okay, so that it will be, or you can use this one to find the frequency like right away, directly in one step if you're interested. If not, it makes no difference in here. So these are, we can say these factors affect the period. But for a mass, we can say for a pendulum here, of course, will the mass, that would be the fourth, let's say, factor here, will the mass affect the period, right? The answer is no, it will not change the period. And the simplest answer is, always look at the equation. If it is in the equation, if there's a variable that is mentioned, if it is in the equation, then it can affect the period. What if it is not in the equation? Yani, it doesn't affect the period, then that's it. So is there the mass in the equation? No, the mass does not affect the period, all right? What about the, because we have angle theta too, we can say, or the amplitude, right? So let's say the fifth one here, the amplitude, you can call it, or you could just call it theta here. Now, does the theta affect the period? So what is your response? Check the equation. Do we have any theta in the equation? The answer is no. So amplitude theta, this one does not affect the period there. And of course, if you want to call the displacement here, that would be the horizontal displacement. Once again, will that affect the period? The answer is, according to this one here, it does not affect the period there. All right, so these are for this, but I want you to be very careful here. For pendulums, we have two things, right? We have the period for the pendulum, and also there is the restoring force as well, right? You know that for the restoring force for a pendulum, these are all the period, yeah? For the restoring force, restoring what? Restoring force in here, you can call it FR if you want to. What is it equal to? It is equal to, in F, G, or F restoring, it is equal to mass times gravitational acceleration times sine theta. We've learned about this before, yeah? So, watch this. If something affects the period, will it affect the restoring force? Not necessarily. So you always have to check the equation. And if something does not affect the period, does that necessarily mean that it does not affect the restoring force as well? No, you always have to compare the factors that are given just to see if it affects or not. We said the length affects the length of a pendulum, it affects the period. But does it affect the restoring force? Right? Does it make the restoring force greater, bigger, smaller? The answer is no, because there's no length in it. Now, what about the gravitational acceleration here? We said it affects the period, right? Will it affect the restoring force? It is in it, right? So, yes, it does. It affects the period. By increasing that, the restoring force increase, decrease this, restoring force decrease. That is the second. What about the frequency? Like, does it directly affect the restoring force? The answer is no, because there's no frequency in it. We're not talking about what happens, for example, if the period changes, the frequency changes, then the restoring and all that. Is there any frequency in the equation? No. So we'll just say directly, it does not change or affect the restoring force. The next thing that we have is the mass. Will the mass affect the restoring force? Your answer is yes, well done, because it is in the equation. What about the angle or theta here? Does it affect the restoring force? Once again, yes, because it is in the equation. These are, we can say, simple and short answers, just to say yes or no. For the period of a mass, we can say for a pendulum, that is both for the period and, of course, for the restoring force in a pendulum too. All right, so now we know what affects the period and what affects the restoring force as well. We simply said because one of them is in the equation, and then, or if it is in the equation, it does affect it. If it is not in the equation, it does not affect it. That is simple answer to whether it affects or not. But here we have a few questions here. It says, What does the period of a pendulum depends on? We said it depends on two things, right? According to the equation, and if not, you could just rewrite the equation so that it is always in plain sight, you could say, or always right in front of you, we can say. Period the square root of length over gravitational acceleration, or ag, doesn't matter, Basha. So it affects on the square root of the length and also square root of the gravitational acceleration. It is directly proportional with the square root of the length, inversely with the square root of free fall acceleration, you can say, right? Okay, so this two here, you can write their relation as well if you want to. Now, the next question that we have says, why does the period of a pendulum depends on the pendulum's length and free fall acceleration? Basha, previously we were saying, will the length affect the period? We were saying yes, because it is in the equation. But what is the true reason behind length affecting the period? Let's find out. Okay, so we have length and free fall acceleration that affect the period. Okay, bear with me. All right, let's go to the whiteboard and explain this one here. Okay. Now, the first thing that we have, by the way, once we're going to analyze or study the effect of one thing on a pendulum, just keep in mind that all the other factors must be constant, should not change. So here's what we have, right? So here's a pendulum. This is the equilibrium position. And let's just, we're basically considering the effect on the length of a period. What? The effect of the length on a period. So at this point here, we can say there are two pendulums, Basha. This is one of them. There's a black pendulum. So that you can see the effect, I'll just draw the same or another pendulum, right? And I'm going to draw that on the same, we can say line here, or the same thing. But if this time, you can see that the length has increased in here. And these are, by the way, the angle is the same. The mass of the two pendulums are the same in here. Every situation is the same. The gravitational acceleration too. So the only thing that is different is now the length of a pendulum. So the factors that we have, we can say the mass is the same, right? So these are, let's say, mass, and then we have the angle theta. What else do we have? We have gravitational acceleration. The only thing that is different here is the length is different. All the other factors must be constant, don't forget, or any other factors that I haven't mentioned if there is any, for example. All right, so now only the length of the pendulum is different because once again, you changed only one variable and see the effect of that on the period here because you cannot change more than one variable at a time and try to see the effect of that on the period because we don't know which, if you're changing two things, if the period change, we don't know what causes this change. So you always have to change one thing, keep the rest the same so that you can see the effect of that. But now, going back to this, so we have different length, right? For this black pendulum, you can say this would be the length, right? For the blue pendulum here, this is going to be the length, right? So, but watch this. If the length of this one is short, how much arc length or what will be, how much or how far is it from the equilibrium position? It is just going to travel this arc length, you can say, if you want to call that one, yeah? But for this blue one here, should have used black there, but doesn't matter, here you can see. But for this one, to get back to the equilibrium position, it has to travel a larger arc length, yes or no? Okay, so this one is larger, we can say, or you can say this is small, but small here. But what brings the mass back to the equilibrium? What brings the mass back to the equilibrium? We said it is the restoring force that brings the mass to the equilibrium, right? So the restoring force for this one here, actually the restoring force, what is it equal to? Restoring force that is equal to mass times gravitational acceleration times sine theta, right? Okay, now, do these pendulums, so we can compare the restoring force of the first and the second. Do they have the same mass? Yes. Do they have the same gravitational acceleration? Yes. Do they have the same angle? And you can see that purposely I've used or draw them on one another. So you can see that they have the same, these two have the same mass, same angle theta, and also same gravitational acceleration because it is done, this experiment is done on the same place. So now these two pendulums have the same restoring force. What does that mean? So imagine or consider, this is the mass, okay? There is a child or a person is pushing this mass back to the equilibrium one, yeah? Now the same person, it is pushing this mass back to the equilibrium too. And which one of these cases do you think the person can reach the equilibrium faster? Of course it is this, because it is the same person using the same force. Let's say it is 100 Newton here and 100 Newton here too. That is the same restoring force, correct? So if that is the case, the shorter the distance, the faster this person, because it is the same force one, yeah? So you're pushing with the same force. If the distance is shorter, then you will get there faster. So we can say this pendulum here, it would take a shorter time to reach the equilibrium. But for this one here, because it is traveling longer, so it takes a larger time to get there. And this is, of course, this is what we have this one, 2 pi, the square root of L over G in here. So by increasing the length here, that would make the period longer or increases the time. But what does the increases the time mean? That means, in other words, if the time or the period for one oscillation is longer, that means it is very slow. That's why the period gets larger. All right, but in our case in here, we said it is going to take longer to get back to the equilibrium. That's hopefully understood this one here. All right, now this is the effect of the length on the period, right? That is first. Now, the second case we have, why would gravitational acceleration also can change the period? Now, I want you to bear with me here as well. Once again, we have a pendulum here. Okay, now this is, all right, this is a mass, this mass that is going to oscillate, okay? So, it is, well, there is a certain angle here as well. Okay, so now this pendulum we're going to copy paste because it is the same pendulum, but it is at a different, we can say, gravitational, or has different gravitational acceleration. Consider this pendulum, it is on Earth. On what? On Earth, where gravitational acceleration G, it is 9.81, right? And then meter per second squared, of course. And consider this one, it is on the moon, where gravitational acceleration, it is 1.63 or 1/6 of that of the Earth's gravitational acceleration. Basha, this is on the moon here. Okay, now, how would this affect the period? By the way, we're changing one thing at a time, right? So that means the length is the same now, right? The mass is the same. The angle theta is the same, right? The only thing that is different is gravitational acceleration. This thing is different for these two in here. So now we know that what brings these masses back to the equilibrium, again, it is the restoring force one, yeah? So at this point here, the restoring force, we can say it is mg sine theta, right? So they have the same mass and the same angle, but because gravitational acceleration here is weaker, so less gravitational acceleration, that means less restoring force. You agree with me, right? So if the restoring force is less, of course, the acceleration of this mass towards the equilibrium, it is going to be very small. In other words, we can say that this mass that is slowly going or moving towards the equilibrium. Basha, if it is bubbling, the force is less, all right? So let's say we have 50 Newton here, all right? Because the force is small, we'll just say 50 Newton. That is just, and like for the sake of the example, let's just say 50. Basha, whatever this, we don't want to. Okay, so in this case here, now the same pendulum with the same angle and mass and everything on Earth, the restoring force here, it is equal to mg sine theta, correct? So now the mass is the same, the angle is the same here, but on Earth, gravitational acceleration is larger, which makes the restoring forces larger, right? So in this case, larger acceleration, larger restoring force. Let's say the restoring force here, it is 100 Newton. Well, this one is just 50 Newton, Basha. And by the way, they have the same arc length in here as well, so we can say same angle theta. Basha, now imagine we have two person, right? One of them it is an adult, a strong person that is pushing this mass with a force of 100 Newton towards the equilibrium. And then there is on the other side here, we have a person who's not as strong as this, that is pushing the same mass, the same, like let's say the same distance towards the equilibrium. Which one of these two do you think can bring the mass back to the equilibrium faster? Well done, you would say this, right? But bringing the mass back to the equilibrium faster, that means shorter period, yes? Or it takes less time. So that'll be the effect of the gravitational acceleration on the period here. So we'll say L over G. So in this case, if G increases, all right, that means period, it is going to decrease. In other words, it is going to get back to the equilibrium at this point faster. If not, if we take a period as a whole thing, so this swing, it is going to take less time to get back to the same point, or the time for one full oscillation will be less here. All right, so these are the effect of increasing the length or changing the length and changing gravitational acceleration on a pendulum. Now, there are more factors actually to consider here. Basha, what about changing the mass of a pendulum or the amplitude, the angle theta here? Why those or these are not affecting the period? So let's take a look at that. Now, regarding changing the mass, this point here, we have two pendulums, Basha. We have two. What is wrong with these pendulums? Let's see if we can, here's the equilibrium position. Okay, and now we have a pendulum, and there is a mass right here. Here is a mass. Let's say this mass is, let's make it small. Okay, so here's a small mass. And then we have the same pendulum. Okay, the only thing that is different is the mass. So what will happen in this case? So same pendulum, the only thing that is different is the mass now. So we'll just make the mass larger. We'll make it larger. All right, so same amplitude and same everything. Remember, we said we can only change one thing at a time. That means the length is the same, and then the angle is the same, right? The arc length or gravitational acceleration is the same. The only thing that is different now is the mass. But watch what happens here. So since the same arc length or angle 2 here, we know that if the mass is small, what do you think will be, by the way, the one that is responsible for the period or to bring the mass back to the equilibrium? It is always the restoring force, you know that. So restoring force in here, it is equal to mg sine theta. Now you can see that the mass, if the mass is small, that means the restoring force is small, right? So we get a small restoring force at this point right here. And then what about this one here, right? This mass is larger, so it is going to so what happened if the mass is larger? Watch this. The restoring force, that is equal to mass times gravitational or free fall acceleration times sine theta here. So the mass and the gravitational or free fall acceleration and angle theta, these are the same in both cases, but here we have a bigger mass. So a bigger mass produces a bigger restoring force, yes or no? Okay, so, but if the restoring force is larger, shouldn't this one move towards the equilibrium faster? We'll say the answer is no, because watch this. If we have a large restoring force, there is a large mass too, yes or no? So this two, you can say, would cancel the effect of one another. What do I mean by this? We know that F net, Newton's second law of motion, equal to mass times acceleration. Yes or no? So the acceleration of this mass, it is equal to F net, all right? Or let's just say for now, let's just call it F net divided by the mass, right? So if the F or the force is large, but the mass is also large, these two would cancel the effect of one another, right? And then let me go to this one here as well. So the acceleration here, it is equal to F net, right, divided by the mass. If the restoring force is small, the mass is small as well. So these will cancel the effect of one another. This two will cancel the effect of one another. We always get the same acceleration here as well. Let's just say 2 meters per second squared, and here would be 2 meters per second squared. So in this case, of course, the mass does not affect the period because they will both end up, moving with the same acceleration towards the equilibrium. I'll repeat this. The restoring force would get larger, right? But the mass is also larger as well. So of course that would need, for example, to accelerate. So this two would affect, or you can say it needs a large force to move to accelerate. So these two, of course, would cancel the effect of one another. So the acceleration for each one of those towards the equilibrium, it is going to be the same acceleration. This is why it takes the same time to get back there. Okay, what does this look like? We can say, watch this. If this is a mass, right, the mass is larger, so it's the same as if a person who's pushing this one is larger too. But larger person pushing a larger mass, all right, it would give it an acceleration, Yani. But then there is a smaller person, or you can say a child, pushing a smaller mass. So these two will end up getting to the equilibrium at the same time, Basha. So here, larger person represents a larger force, but since the mass is larger, so once these two, or the acceleration that this would get will be the same as the acceleration that this would get, because we have a smaller force, a smaller mass, so they could just push with the same or move the mass with the same acceleration, so they will both end up getting the same period. Now the last thing, so you can see that here, it does not affect the period here. Now the last thing that we have, it is the effect of the amplitude or the angle theta on the period here. Okay, so one more time. Now this time we have, again, two pendulums. Let's draw this one. This is the equilibrium position. And here's one of the, let's say, pendulums that we have, right? So in this case, let's just copy paste this one too. Actually, we'll just, we'll do that, because we have to increase or change the angle. If we're going to change the angle, that means you'll have to move this one kind of like a little bit more, yes? So let's say this is the other one. By the way, these angles are too big. This is just for the sake of the example. We kind of like emphasize the difference between the two. So now this one here, there is a certain angle. You could see clearly the difference between these two, yes or no? So this angle, let's call it theta 1, and this is theta 2 here. Now, what is the restoring force in here? Restoring force that is equal to mass times gravity, free fall acceleration times sine theta. Okay, the bigger the theta, the bigger this angle is smaller here. So if the angle is small, then the restoring force is also small in here. What about here? Okay, if the angle is larger, of course the restoring force will be larger too. Remember, all the other factors are kept the same. So what are the other factors? We said mass, right? L, gravitational acceleration. This time theta, it is going to be different, but all the other factors are going to be exactly the same here. Okay, once again, since the angle is bigger, so the restoring force here is going to be bigger as well. But once again, it is true that the angle is bigger, but since the angle is bigger, this distance is also going to be bigger as well. So this one is the same as if, for example, watch this, the restoring force is bigger. So imagine there is a strong person, right, who's pushing this mass. The mass is the same, by the way, okay? But since the angle is bigger, right, this distance that this person needs to push towards the equilibrium is also larger here. Okay, so that is, we can say, what happens here. But here, because the angle is smaller and the distance is also smaller, the angle is smaller, so the restoring force is smaller. It is the same if we have, for example, a person who's not as strong as that one, let's say a child that is pushing the same mass, but let's say through a shorter distance in here. So of course, it is true that this person is going to be very slow to push this one, but because the distance is way shorter than this, they will both end up getting to the bottom or final line. You can call it equilibrium at the same time. Once again, right? It is true that the restoring force is larger, but the distance is also larger too. So larger force, larger distance, they almost cancel. They cancel the effect of one another. They will both end up reaching the equilibrium at the same time. So this is another reason, or the true reason, why the angle or the amplitude here does not affect the period of a pendulum. Don't forget that. That took a lot of time, by the way. And by the way, just to be clear, right, these angles that we're doing or using here, these are, if we're using pendulum as a simple harmonic motion, these angles, all of them, must be less than 15 degrees here, because if it is less than 15, then by increasing, or we can say the effect of increasing the angle theta and the force, then it will be directly proportional. If it is less than 15, that would be a different story. We don't have it in the book, so we're not going to talk about this one either. All right, now going back to this, see, so this is the reasons why does the period of a pendulum depends on the pendulum's length and free fall acceleration. First, Gutman, if we have same pendulum but different length one, yeah, it is even better to draw these pendulums here right on one another. See, if it is here, that would be this much length. There, the longer the length, the we can say the bigger the displacement, you can call it the arc length if you want to here. Okay, so of course, less period for this, more period for this one. Okay, that'll be, just go through, you can go through the explanation here. It says, when the two pendulum have different length but the same amplitude, shorter pendulum will have a smaller arc length to travel through. So because the distance from the maximum displacement to the equilibrium is less, while the acceleration caused by the restoring force remains the same, then both of them have the same force, right? Restoring force. So the acceleration is also the same. The one with a shorter arc length will take less period or shorter period, we can say. What about why the mass and the amplitude affect the period, or why don't the mass and the amplitude does not affect the period? We said when the bob of the two pendulum differ in mass, the heavier mass, of course, provides a larger restoring force, but it also needs a larger force to achieve the same acceleration. So these two will cancel the effect of one another. And this, did you know? You don't have to know it. All right, once again, we said for small angles, don't forget theta less than 15 degrees. When the amplitude of a pendulum increases, the restoring force also increases proportionally, we can say. All right, because the force is proportional to the acceleration, so the initial acceleration will be greater. However, the bigger the angle, we can say the bigger the distance that pendulum must cover, all right? So in this case, for smaller angles, the effect of the two increasing quantities cancel the effect of one another, so the period will stay the same, we can say. So what is important here, just remember this, with small amplitudes, neither the mass nor the amplitude will not or cannot affect the period of the pendulum here. All right, we have another question which is also very important. It's been in Wazari few times as well. So the first question this question that we have says what? A pendulum bob is made with a ball filled with water. What would happen to the frequency of this, or let's say of vibration of this pendulum, if a hole in the ball allowed water to slowly leak out? What is exactly this? Let me tell you what do we have here. Okay. So we have a pendulum. The mass or the bob of a pendulum, it is filled with water. Consider we have a pendulum, right? Here's a pendulum. This bob mass, it is made of something like a water, let's say like a balloon, but filled with water, right? Balloon is not a perfect thing because the shape might change. But here, assume that we have something like a balloon. You fill this with water. Okay, but then there is a small hole in the, let's say this mass, or this bob in here. As the pendulum vibrates back and forth, it slowly leaks out, okay? So what do you think will happen to the mass of a pendulum as the time passes by? The mass will decrease, because more and more water comes out, so the mass of this bob will be less and less. So the question says, what would happen to the frequency of this vibration? Well, there are two methods to do that here. First of all, frequency and period are related. So first of all, period decata to decata, 2 pi radical or square root of L over free fall acceleration. Is there any mass in the equation of the period? No. So the period does not change, right? If the period does not change, will the frequency change? The answer is no. If something affects the period, it affects the frequency too. If something does not affect the period, the frequency will not be affected too. And there is this way you could do it also. Gutmann, frequency, it is equal to 1 over the period, and then you could just replace this equation here. In that case, of course, frequency, it is equal to 2 pi square root of, but don't forget G over L. I don't think this is necessary, but if you just want to use this one here, there's no mass in this equation of the frequency, so frequency will remain the same, or frequency will not be affected, Basha. But what if they change this question, say, and they ask what happened to the restoring force? And by the way, if you're not careful, because this question been in Wazari before, Basha, so next time they might say, what happens to the restoring force? And because you're too, stressed or busy rushing trying to answer questions, you might just think it is still the same question. They're asking what happens to the period or frequency. Period of frequency na agora. But if they ask for the restoring force for a pendulum, g sine theta. So as the time passes, the mass decreases, and so does the restoring force. نقدر بسعر كباسي restoring force the mass will affect the restoring force, and of course it will decrease. Okay, the next question that we have, it is the study tip. Actually, not a question. It says, according to the equation of the pendulum, period decata, 2 pi square root of length over free-fall acceleration. Here's the thing you need to know. We said that the relation between period and length, it is directly proportional to the square of the length. Square root of the length, Basha. And for the period, it is with the gravitational free-fall acceleration, it is inversely proportional with the square root of gravitational free-fall acceleration. But there's one thing you need to know. What happens if we increase the length or decrease the value for g, all right? If we increase this one, the period will increase, yes or no? Or if we make g less, the period will also increase because these are inverse, right? But what exactly does increasing the period means? That means if this pendulum was taking 2 seconds to complete one full oscillation, if we increase the length, now it is going to take longer. Maybe it is, first time it was taking 2, now it is going to take 4 seconds, or maybe 6 seconds, or 10 seconds. So al-muhim, the period, it is getting larger, all right? If the period is getting larger for a pendulum that is swinging back and forth, that means it is swinging slower. Watch this. So where's the pendulum that I had? Maybe over there. Let me get it. All right. So this is the pendulum last time we were using this. We said if, okay, let's just do this properly. All right. Oh, this one is okay, so it's perfectly balanced. Now, we said that, for example, once you let it go at this point, how long does it take to go and come back? That is one, or you can say period, for one full cycle, right? Now, what does it mean if the period gets larger? That means it is just going to swing slower and slower if the period gets larger and larger. Basha, previously, or what does it mean if the period gets larger, by the way? That means the pendulum, or the pendulum swinging, we said it's just going to get slower and slower, Basha. And if it gets slower, that means the clock will run behind. What kind of clock are we talking about, guys? There is previously, you know, like, I don't know, like perhaps decades ago, clocks that we had, it was connected to a pendulum. So the motion of the pendulum were determining like what time it is. So of course, if it was, let's say, oscillating faster, it was the kind of like the time measurement were kind of like faster. But if it was oscillating slower, then the time was going very slow for the pendulum clock, not for the real time we're talking about. We're talking about this kind of pendulum here. So see these old pendulums here. There were like these clocks in here. You can see there are things, of course, to change the setting, or once it slows down, there was a spring there just to so that you can make it swing at the right time in here. So this is the pendulum that we're talking about. This clock was connected to the pendulum. The motion of this pendulum would determine what time it was, not the real time, because when a second passes, it is the same time everywhere, no matter where you are, for example. All right, we're not talking about quantum physics, so let's not get involved into that discussion there. But if a time, for example, if 1 second passes here, the same second passes on the moon, and let's say on the sun, of course, 1 second passed too there. Okay, so if we're talking about this, but these clocks are connected to this pendulum. So if this pendulum swings slower, right, or if the period, so we said if the period gets larger, that means this pendulum, it is swinging slower of a clock. And if it is swinging slower, that means the clock is now going to run behind. Basha, what if it is swinging faster? That means it will take less time for one complete oscillation. And if it swings faster, now the clock, it is going to run ahead. Don't forget that. And of course, I can give you an example too, just to help you understand this one even better. All right, so once again, remember this note. If the length increased or g decreased, the period increases, which means that it takes longer to complete one full cycle. Then the clock will run behind. All right, and then if the length is decreased or g increased, the period decreases, which means it is take less to complete, to finish one cycle. In that case, the clock will run ahead. Also, we can, of course, make questions out of these, and then we'll answer questions that are related to these nodes as well. All right, here we have a question. What does it say? It says, if a pendulum clock, all right, keeps perfect time at the base of a mountain, will it also keep perfect time when moved to the top of a mountain? Your first answer might be just yes, all right, but right, just hold on, not too fast, okay? So in this case, write the equation that we have right here. So we know that period is equal to 2 pi square root of L over g, or gravitational acceleration. Once we take this pendulum, it is the same pendulum, right? And it has the same length, but once you go to the top of a mountain here, we know that is gravitational acceleration on top of a mountain is the same as at the base of a mountain? The answer is no. So we know that, like the further we go, right, to the, or, the further we go away from the surface of the earth, gravitational freefall acceleration decreases, right? So if gravitational acceleration decreases, then of course the period increases. If the period increases, that means the oscillation is going to be very slow, and then the clock will run behind. Basha? All right. Of course, we can reverse this question too, right? What will happen if a pendulum keeps a perfect timing at the top of a mountain? What happens when you go to the base of a mountain? At the base of a mountain, gravitational acceleration is larger, okay, compared to the top in here. If gravitational acceleration gets larger, that is a different question. Then, of course, the period will be shorter. That means the swinging is faster, and in that case, the clock will run ahead. Don't forget. All right, we have another question here, right, which is also sort of similar to this one. It says, if a clock is running slow, how can you adjust the length? Adjust means how can you change the length, okay, of the pendulum to correct the time so that it measures a perfect time here. So don't forget that. Now, what can you do to fix the time in this case? We know that period is equal to 2 pi square root of L over G. Right? So based on this, you can see that these two are directly proportional, yes? So if the clock is running slow, we want to make it go a bit faster so that it corrects the time, yes? But how can you change the length so that it makes the time, in order to make it go ahead, so the time must be shorter, yes? The period must be shorter, right? Once again, the period shorter, that means it is going to cover one full cycle faster. This is how you can do that. So, Basha, we want a shorter time. So what can you do to make the period shorter? By decreasing the length. Yalla, so that'll be the answer to the question in here. All right, how can we correct or fix the time? By shortening the length. The period will decrease, right? And then if the period decreases, that means the clock will run ahead. Basha, what if we reverse this question? What if the clock is running ahead, Basha? If it is running ahead, that means the is very short. It is swinging very quickly. So how can you adjust or change the length to fix the time, right? We can, of course, change this word in here, so the answer will change. In that case, if the clock, let's just make this one, if it is running ahead. All right, if the clock is running ahead, in this case, you will have to increase the length so that the period will be longer, which kind of like it fixes the time or the period in that way. So these are, both of this can be asked, so be prepared for both of them here. Okay, next thing that we have says a simple pendulum can be used as an altimeter on a plane. How will the period of a pendulum vary, that means change, as the pendulum rises from the ground to a final cruising altitude of 1 times 10 to the power 4 meter. So here's a plane as it is rising here. to an altitude to a height of this much, how would the period change? We know that if we go far from the center, then gravitational free fall acceleration will decrease, right? So how would that affect the period? Of course, if this one decreases, that means the period will get larger or the period increases. But the question here is not about whether the clock is running ahead or behind. It is just asking how will the period change. So we'll just say the period will increase, and that's it. What if they say there is a clock or pendulum clock inside that plane? Of course, then the period would get larger, which means it is going to be slower. And if it is slower, the clock will run behind, don't forget. All right, so the period will increase as the plane rises because gravitational acceleration or free fall acceleration decreases. Okay, here's the thing. This question, questions like this, of course, important. It's been in WSAT too. Says you need to know the height of a tower, right? I think. But darkness obscures the ceiling. Darkness, right, blocks the view, or you cannot see the ceiling because of it is dark. So you note that the pendulum extending from the ceiling almost touches the ground. Where does this pendulum come from? Out of nowhere. Okay. All right. So here's the thing. Rasha, here's the ceiling. Let's draw this one. Okay. So here's the ceiling. Right? You can't see the height of a ceiling, or you can't see the ceiling, but you'll notice that there's a pendulum extending. It is almost touching the ground here. Almost. This is touching, actually. We'll just say almost touching the ground here. Okay, so the question says touching the floor and has a period of 12 seconds. How tall is the tower? Do you know that in this case, of course, the length of a tower, it is going to be the same as the height of the building? Correct? Yes. So in other words, because we have the period of this pendulum, we can find the length, which of course corresponds to the height of the tower. So let's do that. All right. So here, it's already here. Watch this. Of course, there's a fast way too, but first let's just do this one. We know that period, it is equal to, what is it equal to? 2 pi radical square root of length over g. We need to find this one, yeah? What is the first thing you need to do? How about squaring both sides in here? Okay, so that is going to be period squared. It is equal to 4 pi squared. It is going to be L over free fall acceleration, correct? So we want the length in here. So make the length the subject. These are going to go below this, under, and then this one is going to be multiplied. In other words, we'll say L it is equal to, or the length, which represents the height in here, we'll say period squared times gravitational free fall acceleration divided by 4 pi squared in here. Okay, so now you just plug in the numbers and you will find the answer, which is the period is 12 squared times 9.81 and then divided by 4 pi squared. Once you do the math, of course, you'll find the answer. And so the length of the tower, the house, whatever that, yes, the length of the tower is going to be 36 meters now. Okay, now, but there is one more thing. I want you to use a calculator. What happens if you divide this two, by the way? Do you know that gravitational free fall acceleration, or 9.81, if we divide that by 2 pi squared, you get almost 1 here, right? So we can say gravitational free fall acceleration divided by pi squared. Rasha, you could do the math, of course, that is almost equal to 1, right? So now, hereafter, anytime you want to find the length, right, of the length of a tower, whatever they're asking for the length, you could just write or use this equation instead, right? So if the question is ever asking for the length, you could just say period squared divided by 4. That would give you the length. But don't forget, right, this g over pi squared, it is equal to 1, right, or almost to 1, only on Earth. So as long as the pendulum is on Earth, you can use this relation, all right? Which all the situations that we have when they ask for the length, of course it is on Earth. But just in case, Yani Basha, if it is on the moon, you cannot use this relationship. You just go back to and use the main equation, which is pretty much not that difficult. You can always start from scratch and do this one here. But if you just want to do it quickly, you can do this as long as it is on Earth. And if it is not mentioned on Earth or Moon, it is always Earth. So it is not on Earth only if a different place is mentioned. Okay. Or if gravitational acceleration, it is very different, which there's obviously no place that could be very different that can interfere or change the answer a lot. Okay, that is regarding this one. Now we have other questions too. So you can see that is there, but don't forget on Earth only. Now we have another question. They also ask about the length as well. So it says, a trapeze artist swinging in simple harmonic motion with a period of what? Of 3.8 seconds. So here's the period. Calculate the length of a cable supporting the trapeze, okay? So here's a trapeze, something like a swing, right? So it has a certain period, and so calculate the length of this one. We said if we want to find the length, we could just do it real quick. Length decata, period squared divided by 4. What is the period? 3.8 squared divided by 4. Then you can find the answer, which is going to be 3.6 meter, and that is the answer. That's it. So I think that is okay to use this one. There's also another question here. It's also been in Wizari 2. It says a visitor to the ancient city of Erbil wishes to find the height of a lighthouse. The visitor ties a spool of thread of a small rock to make a simple pendulum. Then the visitor hangs the pendulum down a spiral, spiral staircase in the center of the lighthouse. The period of the oscillation is 12.1 seconds. What is the height of the lighthouse? We said we could do the same thing, right? So L, it is equal to period squared divided by 4. So that is 12.1 squared divided by 4. You can find the height of a lighthouse, which is 36.4 meter. Okay. That is for this one too. All right, let's do one more, perhaps these questions too. Take a look at this one. It says, calculate the period and frequency. So there are two things, by the way. Calculate the period and then the frequency. Okay, period and frequency of a 3.5 meter long, so this is the length, okay, pendulum at the following locations. The first location we have is the North Pole. Well, G, it is 9.832. So once they, for example, give you a different G, so you can no longer use 9.81, just use the value that they'll give you. So what is the period equal to? 2 pi square root of L over gravitational acceleration. Once again, 2 pi times, what is the length? 3.5? Yes. What is gravitational acceleration? 9.83 and 2 as well. Just do the math, you'll find the period, which is equal to 3.749 seconds. By the way, if you take a look at these numbers, this one has 4 digits, this one is also 4 digits, so you're supposed to keep the same digit or have the same digit as the number of digits that are given in the question. Okay. All right. Now, do the same thing in Chicago, which is gravitational free fall acceleration is there this much. All right. What about in Jakarta, Indonesia? You could try this one too, which is the same work. I'm not going to do that. All right. Here, this question says, by the way, I forgot to find the frequency, by the way. Okay, so you found the period, right? If you want to find the frequency, that is 1 over period. So 1 over 3.749, that is going to be this much hertz. And that is how you do that. So find the period and frequency for each cases. So here's the frequency there. And then, of course, the period for the next one is going to be this much. So this is the frequency. That is the same work. So we're not going to do that. This one here. This is also, you're required to find both the period and frequency. It says a child swings on a playground with a 2.5 meter long, so this is the length, chair, Basha, says what is the period of this child? All right, so in this case, period, it is equal to 2 pi square root of, by the way, if they're not giving you G, you could just use 9.81. So 2.1 divided by 9.81, you could just find the period. Once you find the period, find the frequency too, which is 1 over period, and that's it. It's going to be in hertz. So here's the period, 3.2 seconds. The frequency is this much hertz. All right. Okay, next question says, what happens to the period of a simple pendulum when the pendulum's length is doubled? All right, so once again, don't jump right into the conclusion. If the length is doubled, will the period be doubled? We said the answer is no. Right, we'll just write the equation, put the number into the equation or the relation, then we'll decide. But man, period, what is the relation between period and the length? We said it is directly proportional to the square root of the length. So if the period is doubled, if the length is doubled, so we'll say the period increases by, we can say by the square root of the 2. If not, you could just plug in this number, then we'll say the period increases by 1 point whatever. You could just say this much precisely. So good man, the period increases by a factor of square root of 2. That's it. So here's another question actually. It says, what happens when the suspended mass is, wait a second, what happens to the period of a simple pendulum when the pendulum's length is doubled? Good man, if the length is doubled, it will increase by the square root of 2. Basha. The next question says, what happens when the suspended mass is doubled? So don't say just the radical of 2 again, no. Good man, period has no mass in it, because they got the 2 pi, the square root of L over G. There's no mass in it, so do you think doubling the mass affect the period? No, so the period stays the same. Okay? Once again, if they ask what happened to the restoring force, Kati, the restoring force will be doubled because restoring force, if they were asking, here they don't ask for it, but if they were asking, doubling the mass, of course, because these are directly proportional, so doubling the mass would double the restoring force. Zor Basha. The next question that we have, I think we're almost, yes, says a pendulum that moves through its equilibrium position once every 1 second. It is sometimes called a pendulum's second. What is the period of any pendulum's or second pendulum? Watch this. This question tells you that we have a pendulum, Basha. Now, how many times does it pass through the equilibrium in one full cycle? 2 times, correct? Well done. So 1 time, here is consider my tie is the equilibrium. So 1 time to go, and yeah, that is 1 time passing through the equilibrium, and then the other time it is coming back. So passes through the equilibrium 2 times. Just see, maybe I can use the pen to do that. So watch this. So imagine if we start from one of the side here, right? So if we start now, that is 1, 2, in one full cycle. I don't know, like we have to use a reference point. Once again, I think my tie would be the best to use that as a reference point. So imagine my tie is the equilibrium position. In one full cycle, it has to go and come back How many times does it pass my tie? So that is 1 to go, 1 to come back, so 2 times. But the question says, every time it passes, it takes 1 second. And then, so 1 second to go, and 1 second to come back. So what is the time for one full oscillation? 2 seconds? Well done, you got it right. And that is the whole idea in this question. If you understand this one, that'll be perfect. Okay, so now, one more time. Let's draw this one too, just in case, if there's a person who didn't understand this so far. We have a pendulum. Here's the equilibrium position. We can start at this point here. Now, how many times does it pass through the equilibrium in one full cycle? 2 times, because 1 time for going and then 1 time for coming back. Basha, if it takes 1 second to go and then 1 second to come back, so what is the time, or what is how long did it take? That would be the period one, But man, the total time it takes to go and come back, it is 2 seconds. So that will be the period of this pendulum, which is called seconds pendulum. If the period is 2 now, whatever they ask for, we can find that. So the first part says, what is the period of any seconds pendulum? What is the period of any pendulum that is like this? The period is 2 seconds. Basha. The second part says, in Cambridge, the seconds pendulum is this much long. What is the free fall acceleration? Basha, write the equation. Period decata, 2 pi. radical over square root of L over gravitational acceleration. The question says, what is G? So we have the period. What is it equal to? It is 2. It is equal to 2 pi. The square root of L over, what is the length, by the way? We have the length 2. How about we just square them first? Let's just square them. If we square them, we'll get rid of this square root in here. So period squared, they got the 4 pi squared L over gravitational free fall acceleration. All right, since we did this one, you could now plug in numbers, or you could do one more like step in this case. Can we just replace this one? Yes. If not, go ahead and do the cross multiplication. So in this case, we can say gravitational free fall acceleration at Cambridge, or whatever the location is, it is going to be 4 pi squared times the length divided by period squared. Basha. All right, 4 times pi squared. Plug these into your calculator. What was the length? It was what was it? It is 0.9942. You can see that is the length, 0.9942. And then the period was 2, but don't forget this period is squared in here. Now do the math, of course. You'll find gravitational free fall acceleration, which is 9.812. So gravitational acceleration is now it is 9.812, I guess, right? Yes. That is going to be meter per second squared, since it is gravitational acceleration. So that will be the correct answer here. Okay, now the next part says what? It says in Tokyo, Japan, the second pendulum is this much long. What is the free fall acceleration? So this is the same work. Because it is the same work, we're not going to do that. But if you're interested in the solution, here's the solution. The last question, perhaps for now, says, what is the free fall acceleration in a location where the period is period of this much long? What is the idea in this much, Baba? So be careful, right? It says where the period of a this much long pendulum is this much. So don't forget, just because this number comes after period, that doesn't mean this is the period, Baba. Always look at the unit. It says the period of this much long. So this is the length of a pendulum. So the period, it is equal to this much seconds. So this is the period, which I believe everybody's, know enough to differentiate between this. Basha. So now, can you find the free fall acceleration? We said yes. Period again. It is the same, by the way, as before, but we're just going to do that. 2 pi square root of L over gravitational acceleration. You could square both sides. So period squared, they got the 4 pi squared L over gravitational acceleration. But by the way, if you don't know how we did this, you can write this way here. You could write all this in 4 pi squared times L over G. Now, perhaps it might be easier just to see how or why you swap them. So gravitational free fall acceleration, they got the 4 pi squared times length divided by the period squared. You have the length, you have the period, and then you could simply just replace or plug in the numbers and find the gravitational free fall acceleration, which is going to be 9.7 meter per second squared. All right, that'll be the end for today. This question, because this is something very important, we're going to do this next time, inshallah. So that'll be the end of this session. Keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.